In this video, I'm going to derive the Schrödinger time-dependent equation based on only one assumption. For this video, you'll need to know the Dirac-Bra-Ket versions of complex vectors and linear algebra, and a bit of calculus. There's plenty of videos online about these things, so once you have that mastered, you can come back and see this derivation. If we have two basis vectors, two complex vectors that represent states from which we can build any other state in this system. For example, with an electron spin, the two basis states are up and down. Every other state of spin can be shown as a linear combination of these two states with coefficients that are complex. If we take two of these basis vectors, we know that if they are distinct, their inner product will be 0. If they are the same, however, if psi and phi are the same basis vector, they'll equal 1. So we can represent this through a Schrödinger delta. Now here's the assumption that I talked about earlier. We will assume that if these two basis vectors are completely separate in this way at time 0, in which case they equal the Schrödinger delta as before, they will be separate in the same way at any later time. In other words, basis vectors may evolve, but they never lose their orthogonality, or lack thereof. Now, with this assumption under our hand, we can create some operator u of t that when it operates on a state psi of 0, it gives back psi of t, the evolution operator. The same thing will apply to the state phi. If we take the Hermitian conjugate of this equation, we find that phi of 0 with the Hermitian conjugate of u is equal to the Bra version of psi of t. Since we have this equation over here, we can multiply these two expressions and come up with the same relation. In other words, phi of t, inner product with psi of t, is the same as writing phi of 0 times the Hermitian conjugate of the u operator, just the same as the Bra version of psi of t, multiplied by u of t psi of 0. We know this has to equal the Schrödinger delta of phi and psi. If phi and psi are the same, this must equal 1. But we already know that phi and psi at time 0 will equal 1 regardless of whatever operator is between them. If this wasn't part of our equation, the inner product of psi 0 and phi 0 would still be the Schrödinger delta of phi and psi. Similarly, if they were different or the same operation would take place, in which a difference between them would still be the Schrödinger delta. It would still equal 0 when we take the inner product. If they're the same, an inner product will equal 1. As you can see, this expression and this expression have the same value in every case. The only operator that we can place between phi of 0 and psi of 0 to have this effect is the unit operator. In which case, this term right here must equal the unit operator I. Because of this, we say that time evolves in a unitary fashion. Now, we can derive the Schrödinger time-dependent equation. Let's assume, from what should be obvious from classical mechanics, that systems evolve continuously. In which case, we can write the unitary time evolution operator as I. In this case, we'll make a term complex number I epsilon h, where t is epsilon. T is a very short time after time 0. What this means is, after a very short time of time evolution, the system will only change by a small amount, this, from its initial state, which is given by the unit operator. We can also write the Hermitian conjugate of this equation. The Hermitian conjugate of the unit operator is just the unit operator. We have to conjugate the complex term and conjugate h, whatever operator that may be. Now, we know that u, dagger u, is I, which means that I minus I epsilon h times I plus I epsilon h dagger must equal I. When we FOIL this out, we get I squared minus I epsilon hi plus I epsilon I h bar plus epsilon squared h dagger equals I. In this case, we're assuming epsilon is small enough so this term doesn't matter and goes to 0. In which case, I minus I epsilon h plus I epsilon h bar equals I. From this, we can see that h bar minus h dagger minus h multiplied by I epsilon is equal to 0, which means h dagger is equal to h. Because of this, we know that h must be an observable quantity. Observable quantities are always represented in quantum mechanics by Hermitian operators. In other words, the Hermitian conjugate is equal to their original form. So, let's take a look at what this means for unitary evolution. I minus I epsilon h, which is the unitary operator, multiplied by psi of 0 equals psi at epsilon. If we expand this out, we know that psi of 0 minus I epsilon h psi of 0 is equal to psi at epsilon. If we rearrange the terms, we find that psi at epsilon minus psi at 0 divided by epsilon is equal to, if we look over here, negative IH times psi at 0. If we take the limit as epsilon approaches 0, this becomes the derivative, the time derivative of psi. Now, if we multiply both sides by positive I, this I will cancel, and we have h of psi equals I times the time derivative of psi with respect to time. Now, if we factor in a factor of h bar in order to make the dimensions work out, the units, we find h of psi is equal to I h bar d psi dt, which is, in fact, the time-dependent Schrödinger equation. When we find what h is, it turns out to be the observable energy. The reason we represent it as h is because of the Hamiltonian, which is a term in classical mechanics that represents the total energy of a system. That's all for now.